Hello and welcome. We continue yesterday's lesson where I gave some questions in turning effect of a force. I also looked at the calculations that we go through when we are looking at the topic equilibrium and center of gravity. I gave you a few examples, and today I want to start today's lesson by looking at one of the questions which I gave as an assignment. I asked you to do it. So let's see how it is worked out. You may mark your own work going by or following the concepts which we are going to discuss in this particular lesson. So let's look at the question together. Now here we are told that the diagram below shows a metal plate 3 meters long, 1 meter wide, and negligible thickness. So it is a lamina. This is what we refer to as a lamina. A horizontal force of 100 newtons applied at point D just makes the plate to tilt. So this plate is in equilibrium. It is just about to turn. So still that is equilibrium. So the principle of moments must apply. Calculate the weight of the plate. Let's start by looking at some of the information that we have here. Since it has negligible thickness, this is a uniform body, and for any object which is described as a uniform object, then we have already agreed that its center of gravity is at its geometrical center. Let us look at some of the ways in which we determine the geometrical center of some uniform bodies. You're already familiar with the meter rule. A meter rule is 100 centimeters long, so its center of gravity is at the 50 centimeter mark. If you're given a rectangle such as this one here, the center of gravity is at the point where the diagonals are going to intersect or to meet. So if you draw a diagonal from this point, you put a ruler here and then you draw a line here and then a line here. You're drawing diagonals. Where they meet is where you expect to find the center of gravity. So this must be the center of gravity, the point of intersection of the diagonals. So that means that from here to here it's 1 meter divided by 2. And from here to here is also 1 meter divided by 2. Similarly, from here to here is 1.5 meters. And from here to here is also 1.5. Because I get this length, I divide that length by 2 and I get 1.5. I divide this length by 2, I get 0.5. Depending on the kind of distances that we might be asked to use. So let us say that this distance here, let me just draw a solid line. Solid line is much better. So this distance here this other distance here is 1.5. meters. That is the center of gravity of this regular body is 1.5 from this surface and 0.5 from this other surface. So, and I've already explained how you get it. You just draw diagonals. You put a ruler here, you draw this line. You also draw this line here. These are diagonals. The point of intersection of the diagonals will be this point. Similarly, you know that since this one is a regular lamina, then that center of gravity is at a distance which is halfway this length and halfway this other length. So depending on what you are looking for, that is how you can determine the center of gravity of this particular object. Next, we know that since we have been able to determine that this is the center of gravity, or the G, then it means that the weight of this object acts through that point. So it acts through this point. So this is the weight of the object. And it is what we have been asked to calculate. Calculate the weight of the plate. Let's call it W. W. What are the forces acting? There is this force of 100 newtons and there is this other force of W newtons. And this system is in equilibrium. Otherwise, it will turn about point A. Point A is the turning point. So, what do we do here? Since the system is in equilibrium, we are going to take moments about point A. And we are going to say that clockwise moments, that is a sum of the clockwise moments should be equal to the sum of the anti-clockwise moments. We are taking moments about point A. That is what we are doing. Moments about point A, then that is what we get. Let's look at the forces acting. This is a 100 Newton force, and you can see that the distance which makes 90 degrees with the line of action of the 100 Newton force. You know, you have to identify the forces acting so that you can find the moment due to those forces. So one of the forces acting is this 100 Newton force. And its line of action is this one here. This is the line of action of the 100 Newton force. And you're taking moments about point A. So you find the distance from A, which makes 90 degrees with that line of action. And it is this distance, and it is 3 meters. This 100 Newton force will tend to turn the system clockwise about this point. I've already explained how you get the direction of a given moment. So it will tend to turn that system clockwise. And it is the only force which tends to turn this plate clockwise about this point. So when it comes to clockwise moments, we are going to say it is 100 times 3. Let's look at the anti-clockwise moments. The anti-clockwise moments is due to the weight of the object, and it will tend to turn that system anti-clockwise about this point. What is the line of action of the weight? This is the line of action of that weight. This is its line of action. What is the point about which we are taking moments? It's point A. And what is the distance from A which makes 90 degrees with the line of action of W? What is that distance? It is this much, and it is 0.5. So we are going to say this one is going to be equal to 0.5 as the distance times W. And we are going to see that this one will be 300 is equal to 0.5 W. We divide both sides by 0.5 and our weight will give us, our answer will be 600 newtons. So it is just as simple as that. What would we be looking at when we are looking at this particular question? Many times when you are given a diagram, do not be afraid to include some measurements on the diagram, because the examiner can look at that. In fact, looking at information given on a diagram becomes very easy for the examiner rather than written work. So ensure you do something sensible on the diagram. But of course, it should be directed by the question. If you're asked to show something on the diagram, then don't fail to show it, because that one earns your mark. If a diagram is given and you're making reference to it, you can draw something there, you can put a point there, and then make reference to it when you are calculating anything which is asked for. So this is how you would work out that question. It is so simple. So clockwise moments equals to anti-clockwise moments. But if this question is given 3 marks, then 2 marks, 2 full marks would go to this particular substitution here. This substitution. And then 1 mark goes to this answer here. And that is how you can mark your own work. So I hope you've gotten the question correct. If you never got the question correct, then I've explained how the answer is arrived at. Why don't we go back to that particular chapter and look at more questions in turning effect of a force, because I'm sure when you look at the exercises, there are more questions. So let's go ahead and look at more questions in that exercise. Now, if you go to the revision exercise in the chapter Turning Effect of a Force, question 3, you will find this particular question. The diagrams below show uniform bars balanced about their centers by different forces. Calculate the unknown distances and forces marked in each case. Now, the diagrams I've drawn here may be slightly different from the ones which is in your textbook. The distances are a bit different, but the concept is the same. So I'd like you to concentrate on the method that we use to solve the question rather than the exact answer. All right. So let's look at this. Here we've already been told that these bars are balanced about their centers. What does that mean if they are balanced about their centers? Now, that means that if it is balanced about its center, that is the center of this bar is here. That means that that is where the center of gravity is, and that is where its weight acts through. So when we take moment about the balancing point here, or the point where the system balances, the moment due to the weight of that bar automatically becomes 0, so it does not feature anywhere. I want to repeat that because it is very important. These bars are balanced about their centers. If they are balanced about their centers, they are balanced at the point where the center of gravity of that bar is found. What is center of gravity? It is the point through which the weight of the object acts. And since it's the point through which the weight of the object acts, and we are taking a moment about that particular point, the moment due to that weight becomes 0, because the distance, the perpendicular distance from the turning point all the way to the line of action of the weight is 0. So any number multiplied by 0 is 0. That is a very important concept. Very important concept. So always ask yourself, where is the bar balanced? Have they told me that it is balanced at its center so that I can ignore the moment due to its weight? Or is it balanced at some other point so that the weight of the object has moment about that other point? Or have I been told that the weight of the bar is negligible so that I do not consider the moment due to its weight? Those are some of the things that you look for when you're looking at this type of question. So now the other thing is that these bars, they are balanced. Since they are balanced, it means the principle of moments must apply. So I'm going to take moment about this point G, or you may call it point O, and realize that the moment due to the 120 Newton force is clockwise. The moment due to F1 is anti-clockwise. And also the moment due to the 40 Newton force is also anti-clockwise. So there are two anti-clockwise moments. So I'm going to put an equal sign here. And then I'm going to say clockwise moment due to this is equal to the anti-clockwise moment. Of course, here I'm talking about sum. Sum of the anti-clockwise moments equals to sum of the clockwise moments, although there is just one clockwise moment. So let's again put the equal sign here, and then we start with this one here. This one will be, the force will be 40 newtons times how far it is from here all the way to this point, which is 12 centimeters. Of course, that 12 centimeters I can divide by 100 to convert the 12 centimeters into meters. But we're going to see that that is not necessary, just like we saw in the other video. The other anti-clockwise moment is due to F1 times how far is it from the turning point. It is this much distance here, which is 8 centimeters. So this one will be 8, again divide by 100. The clockwise moments will be due to 120 times 5. Again, I divide that by 100. And you can see if I multiply both sides by 100, you find that this 100 will cancel out with this, and this one will also cancel out, and also this one will also cancel out, so that I'm left with the 40 times 12, which will be I think 480 plus 8F1 is going to be equal to, I think, 600. And you can be able to work out F1. How do you work out F1? We're going to subtract 480 from both sides, and you're going to find that on this side I'm going to have 120. 480, yes, 120. So that to get F1, I simply need to divide 120 by 8, and you get your force here in newtons. I think that one is pretty simple. You can just get your calculator and get that value. That is how you would solve that question. Remember, the question that I'm trying to solve is found in your course book. I've just made a few changes so that the distances make sense. I've also changed the magnitude of the forces so that we can have large forces to deal with. So that is the only difference that I've made. Let's go to the next question. In part B, again, this bar is balanced about its center, in which case this is the center of gravity. The weight of the object acts through that point, and because it's balanced about that point and we are taking moment about that point, the moment due to its weight about that point becomes 0. Automatically it gets eliminated from the calculation. So again, we're going to see that the clockwise moment is due to the 100 Newton force. The anti-clockwise moment is due to F2 and 25 Newton force. Notice that forces do not have to be on the same side of the turning point to turn the system in the same direction. Forces, it's not necessary for the forces to be on the same side of the pivot for them to turn the system in the same direction. And we have seen it in this example. Look at F2. F2 is on the same side as the 100 Newton force. But while with the 100 Newton force turns this bar clockwise about this point, the force F2 turns it anti-clockwise. So when it comes to the sum of the anti-clockwise moments, it will be the F2 about this point plus 25 newtons about the same point. I'm going to add those two. They turn that system in the same direction, although they are on opposite side of the turning point. So it is important that you realize that. So the clockwise moment again is due to 100 times 120 centimeters. This time I'll avoid dividing by 100 because we have seen what happens. The sum of the anti-clockwise moment will be, this one will be 25 times how far it is from the pivot, and that is 6 plus F2 times 5. Again, you can see the only force which is unknown is F2, and we can be able to work it out. From here, I know you can be able to multiply. You can be able to know what to do when it comes to, like for example, when you get this value here, you'll have to move it to the other side in order to subtract it from that value so that you can divide both sides by 5 in order to get F2. I hope you're going to get a positive value for that. Let's look at part C. Part C, again the same bar or this bar is balanced about that point, and that point happens to be the center of gravity. Remember, this is not always the case. It's not necessary for you to balance the system at its center of gravity. It depends on what you've been told in the question. In this question, we've been told that the bars are balanced about their centers. And that is why we are doing what we are doing. So, the moment due to the weight of this object above that turning point, of course, becomes 0. So we forget about that. 18 Newton force. Actually, in your textbook, you'll find that this 18 Newton force in your textbook is 1.8. 42 Newton force in your textbook is 4.2. But I've just decided to change a few values so that you do not just concentrate on the final value, but you want to know what is the method that is used to solve this particular question. The moment due to F2 about this point is also clockwise, so there are 2 clockwise moments. How about 36 Newton force? 36 Newton force tends to turn the system anti-clockwise about this point, and so is the 50 Newton force. It tends to turn that system anti-clockwise about the same point. Now, the other point to emphasize here is distances are always measured from the same point. In fact, when we state the principle of moments, we say that if a system of forces is in equilibrium, the sum of the clockwise moments about a given point is equal to the sum of the anti-clockwise moments about the same point. In other words, we take moment about the same point, and you're going to see how this one translates. So the clockwise moment, I'm going to put an equal sign here, and now I'm going to have clockwise moment as being 18 times 4, that one there is no problem, plus 42 times, I know some of you have said times D. No, it is D plus 4. Because when we take moments, distances are always measured from the same point. So what is the distance that makes 90 degrees with the line of action of the 42 Newton force from this point, not from here, not from here. So this one is always a trick. The examiner always gives you this to find out if you can be able to apply that concept that all distances are measured from the same point. All distances are measured from the same point when you are dealing with the principle of moments. And the moment you have realized that trick, is just a matter of now on the other side you're going to have 36 times 2, and of course here we are going to have 50. So on this other side you have 50 times the distance 8. And again, I don't think I need to proceed further than that, because the rest of it is just use your calculator, use simple mathematical manipulations, and you'll be okay. Maybe the point I want to emphasize here is that here you must open the bracket. You must multiply. Everything will be okay, but when it comes here, you must open this brackets and say 42D plus this times this, you're going to get it is 168. This is how this part will look like. Okay, you'll have to open the brackets. So 42 times D plus 42 times 4. You get that. The rest of the working out is just using the calculator. Multiply those values, and then you rearrange the numbers so that you can see how you can divide by 42 throughout to get the value of D. And that is how you solve such simple questions. I want to challenge you to go back to that exercise. When you go back to that exercise, you'll find some questions which are at the end. Let me just show you those questions. These questions here, from number 5, 6, 7, 8, and 9, and even 10. Can you be able to give me a solution to those numbers from number 5 to 10 as some kind of an assignment? Remember, when you do assignments, when you do questions which the teacher has given you, it gives you a chance to test whether you have understood. Do not skip any assignments which are given by your teachers in school, or even if it is in an online lesson like this one. I know you're watching this video on YouTube, and it appears to be very easy when I'm solving these particular questions here, but do not be deceived by that. Sometimes questions can appear to be very easy when somebody else is doing, but when you are doing it, you actually discover it was not as easy as the way the teacher was doing it. So through that, you get to learn what is it that was giving you a challenge. You get to understand that there were some points that you actually didn't understand even when the teacher was explaining. So I'd like you to take a moment, maybe about, this one can take you about 45 minutes to go through them. If you do not have this textbook at home, just pause the video. Let me see whether I can enlarge this. No, I think if I enlarge it moves out of the screen. Just pause the video, copy down these questions in your notebook, then solve each one of them, and then in the next lesson I will show you how each one of those questions is solved. That is how you learn, and I'll see you tomorrow in another lesson like this one around the same time. Bye bye.